Hi everyone, we're iSee. Our project focuses on creating accessible gaze-based technology for iPhone users with limited mobility. I'm Beverly and I lead software research and development. Yi focuses on user research and interaction design, and Joe on hardware. Let me start by introducing our client. Meet Jessica Frew, a model, actress, and disability advocate born of cerebral palsy that limits her upper body mobility. Since age 9, she's used eye gaze technology to communicate and control devices. Jessica leads an incredibly active life, but struggles to find assistive technology that balances portability with precision. Here's the problem: Jessica needs mobile eye gaze with desktop level precision. The iPhone's built in eye gaze has terrible tracking accuracy, making it essentially useless. Desktop solutions like Toby works great, but they're bulky and impractical for mobile use. No existing solution bridges this gap. We've identified two technical barriers. First, icons are too small. Densely packed mobile screens make accurate selection impossible. Second, lighting challenges. Current systems fail in sunlight, dim lighting, or changing conditions, losing calibration mid use. Our project aims to answer: can we bridge the gap between mobile portability and professional grade eye tracking by addressing both hardware limitations and interface design? Our approach consists of two parts: a physical hardware prototype to address lighting challenges, and interactive Figma wireframes with enlarged icons and optimized interfaces, plus a web prototype to validate UX concepts. To ground our designs in real user needs, we begin our comprehensive research. Yi will now walk us through our research findings.
Since then, I will begin with our research. Our first phase focused on user-centered insights, and you can see two images from our session with Jessica. One shows her eye tracking control menu, a circular mounted file with tiny icons that appear when she focuses her gaze. The other shows her using a communication keyboard during a video call, typing entirely with her eyes, meeting her grounded our project in reality. We saw challenges that really show up in documentation: calibration sleeping under bright light, the struggle of selecting small icons, and the eye fatigue that builds with prolonged typing. She even shared her own idea for an iPhone setup, and let's show that bottom part. We mapped a simple user flow shown on this slide to visualize how eye-only navigation moves through selecting, scrolling, and conforming. In phase 2, we conduct a competitive analysis of systems like Toby and PCI. They are reliable but still face issues with outdoor lighting, calibration precision, and long-term comfort. Phase 3 was a deeper dive into Jessica's specific concerns: larger icons, clear feedback before selection, and reduced effort across screens. At the top of this slide is WCAG contrast chart, paired with a green check and red X icon that show how color and shape improve clarity. We also touched high versus low contrast with the table shown on the slide. High contrast around 7 to 1 significantly improve accuracy, while low contrast around 3 to 1, especially in bright environment, leads to more misdirection. Together, these phases create a foundation shaped not only by research, but by lived experience, revealing what users truly need to feel confident and comfortable with eye tracking. I will now hand it to Joe for our prototype design.
Hi everyone. My process followed three main phases: ideation and sketching, prototyping the hardware, and how to conduct user testing with iterative improvements. Phase 1: ideation and sketching. A few key decisions guided the technical direction. I selected a global shutter camera to avoid motion blur, which is essential for pupil detection. The Pi Zero 2W offered the best balance of size and computing power. After encountering OS issues with CSI cameras, I switched to a USB camera for reliability. Power stability was addressed using a compact 5-volt power bank. Phase 2: hardware assembly. I assembled the Pi Zero and a USB global shutter camera, tested angles with a temporary rig, and confirmed a power bank works for early use. The prototype image on this slide is a hardware mock-up showing how the camera mounts above the device, allowing early testing of angle, field of view, and user comfort. After trying multiple enclosure ideas, I chose an adjustable car phone holder for stable, flexible positioning. Phase 3: user testing and ideation. Because the project involves collecting eye images, which qualify as identifiable biometric data, user testing must be reviewed by the IRB. Post IRB, To evaluate performance, I would conduct informal testing with peers. I would measure image clarity, glare resistance, and pupil tracking stability indoors and outdoors. Note that Jessica highlighted that outdoor lighting was the biggest issue with the Tobii eye gaze tracker. I believe the sunlight overwhelms the sun's sensor and reduced contrast. A major achievement of this project was developing detailed CAD models that guided the hardware design. I modeled the full eye tracking assembly, camera, Pi Zero housing, and the mounting system, and created a compact clip on phone mount that positions the camera at an optimal angle. Future CAD iterations will integrate optical elements like a flower style lens hood to support outdoor performance. Beverly will now go over the software research.
Thanks, Joe, for walking us through the hardware prototype component. Now, I'll cover our software exploration, which happened in 3 phases. Phase 1, we built a browser-based prototype using WebGazer.js to simulate gaze interaction. This includes calibration, dwell selection, and feedback. This validated our core UX patterns and proved conceptual feasibility. Phase 2, we researched building a custom iPhone app with system-wide control and improved calibration. But we hit major roadblocks. iOS sandboxing blocks third-party system control, and TrueDepth camera access is heavily restricted. Apple's built-in eye tracking seems to be our only option, but Jessica confirmed that it doesn't meet her needs when we reached out to her again. This brings us to phase 3, our conclusion. Third-party iOS control is technically impossible, but this research was valuable. With it, we documented viable paths for Jessica and validated interaction patterns. The key takeaway from this is that software alone can't solve her precision needs, which reinforces our hardware prototype approach and directs our focus towards designing a better interface for Jessica. Our web prototype from phase 1 still remains useful for demonstrating interaction logic. Yi will now walk you through our iOS app designs and how we optimize them for eye gaze interaction.
Thanks, Bear. We began shaping our iOS app. In ideation, we built a design principles table grounded in Jessica consent and WCAG guidelines. That led us to a few key choices, like the target size, high contrast visual around 7 to 1 with bright icons on a dark background, and a clear two-step gate interaction, where you should first highlight and then confirm to avoid accidental selections. In visual design, we chose a black background with white text to reduce eye fatigue, especially in bright environments. The blue halo became our gaze indicator because it's high contrast, accessible for users with color vision differences, and already familiar in iOS as a focus state. On this slide, you will see how feedback works. A soft blue halo appears when the user begins to gaze, and it gradually shrinks over about a second to confirm the selection. Our lo-fi prototype walks through that flow shown on the slide, gazing at the message button, entering the inbox, and using the magnifier to zoom into a conversation within large text for easier reading. When we shared this with Jessica, she emphasized how much it depends on symbol boards, keyboard boards, and save phrases. In our final prototype, you can see that reflects in the typing experience you will see in the video.
Hello everyone, this is the iSee iOS app design demo. Our focus is making eye gaze interaction easy, accurate, and comfortable for users. In this demo, you'll see our simplified home screen with 3 to 5 main features, and we'll walk through the messaging flow with the communication keyboard. When the user opens the iPhone and gazes at the message icon, a soft blue halo appears. Holding the gaze for about 600 to 1000 milliseconds confirms the selection, and the user enters the Messages app. From there, they can gaze at the magnifier button to zoom in and read message details more clearly. Inside a conversation, gazing at the text input box triggers the communication keyboard. Users can type using enlarged, easy-to-hit keys, and then select from suggested phrases that appear above the keyboard. They can also choose from categorized phrase boards, allowing quick access to customized and frequently used expressions. Once a phrase is selected, it fills into the text box, and the user returns to the dialog view to send or continue the conversation.
Now I'm moving to Joe for the next steps.
To finish off, I'll be going over suggested next steps. These include calibration plus gaze mapping, IR illumination, enclosure refinement, algorithm improvements, and user testing and open source preparations. The team and I would like to say thank you for listening to our presentation, and we hope to see future improvements.